When we first started talking about these volumes of revolution, we ran into the disk method, or more specifically, the washer method. The first picture that we drew was probably something like this. We had this region here, and we said that we were going to revolve this around the x-axis. Now, the first time we saw this, I talked about area, and that we would have a representative rectangle put in place like that, which gave us a little piece of dx. However, there was no reason I had to put the representative rectangle perpendicular to the axis of rotation. I actually had the option to actually put the representative rectangle parallel to the axis of rotation. In this case, that would actually give me a little piece of dy. And then we would rotate that around the axis exactly like before. But the difference is what shape we end up getting. If we take this and rotate this around the x-axis, the shape we actually get is more of a long cylinder like this, or a tube, or a shell is what they call it. Because remember, this width right there would be infinitely small, so you just get these infinitely small shells that get smaller and bigger and bigger and bigger until you get all the way to the outside. So just like before, we need to say, okay, hey, what would the volume of one of these little shells be, and then add them up in whatever direction that we're moving. Now, we can actually cheat this a little bit, and I'm going to kind of show you where this comes from. This isn't exactly the derivation, but you can definitely see that it would make sense. With our washer method, our shape looked like this when we rotated it. Like this. And we had this hole in the middle. And for our washer method, remember from our center line here, out that way, we had the big R, that was the distance from the axis of rotation to the outside edge, and little r was the distance of axis of rotation to the inside edge. And that looked like this. It was pi big R squared minus little r squared d something, dx, dy, whatever it was, depending on which way we were rotating. Well, I'm going to do a little bit of algebra with this, and I'm going to show you how this shape can turn into this shape. First off, hopefully you can see that that's the difference of squares. So that would be big R plus little r, big R minus little r, d something. Have an idea there. All right, so let's see what happens here. How do I turn this shape into this shape? Now, just for notation's sake, remember this could be dx or dy. Remember this side here was our dx, so I'm going to go ahead and just call those x's. It could be in either direction, but just for our picture. Okay, so what happens to this to turn it into this? Well, this side here, dx, turns not from something that's infinitely small, but something that has length. So for a cylinder, let's call that the height. So the first thing that's going to change in our formula is this dx is going to turn into an h. Now, you can call that the height of the cylinder or the width of the cylinder. What happens here? Now remember, we have our rotation line going right through the middle here, and big R and little r are really harder to see. Big R goes to, of course, the outside edge, little r goes to the inside edge. Now for this to get dy, the way I have it in this picture, get it squeezed farther and farther and farther, that means little r has to be getting closer and closer to big R. So, and here's where a little bit of hand waving, this is why this isn't perfect like this. Since little r is getting closer and closer to big R, that means these two are getting closer and closer to the same value. So I'm going to go ahead and say if we get infinitely close, that turns into just 2 big R. Now, here's where the hand waving really happened. What does this become then? Well, that would become 0, right? Because little r is getting closer and closer and closer to big R, so that's becoming infinitely small. Or that's becoming a differential. Now, since we're in the way I have this picture drawn, since that ends up squeezing it this way, right? It's going in this direction. I'm going to call this piece here a little dy, and we have an h. So in this case, we have 2 pi big R times h d something. I'm going to go ahead and call it dy. All right, now notice that our method here changes. Now we have 2 things that we need to show. From our original picture, if we're going to rotate around this way, we need this distance here, which you can call a height or a width, and you need this distance here, which we call the radius. That would be the distance from the axis of rotation out to the representative rectangle. Okay, so the washer method and the shell method are very closely related. It's basically the same shape stretched in a different direction. So let me go ahead and define what R and H are in this formula, and we'll see how to apply it. All right, H here is the height or width, whichever way you want to look at it, of the representative rectangle. And big R is the, oops, there's a T there, is the distance from the axis of rotation to the representative rectangle. All right, so let's actually set up and take a look at something that we did last class, and we'll do it roughly the same way again. So let's define our region. So find the volume generated by revolving the region, the bounded region, about the given axis. So exactly the same directions that we got when we were doing the washer method or the disc method, whatever you're talking about. So let's kind of do this picture here. Let's say we have y is equal to the square root of x, y is equal to 0, and x is equal to 4, let's say. So again, exactly like before, we're talking about our volumes of revolution. You want to sketch the region. So over here, this is x is equal to 4, which means that would be y is equal to 2. Okay, so there's our bounded region, kind of like the picture I just erased. And let's say that we're going to go about the x-axis. Let's do a couple here. Let me change this. Let's go about the x-axis for one, and then we'll go maybe about the y-axis. All right. So about the x-axis, so for my picture, it goes this way. Now, which way do we draw our representative rectangle? Well, for this method, the representative rectangle is parallel to the axis of rotation. Now, that's kind of how we defined it originally, so that should be kind of implied. So when I draw this, there is my representative rectangle. And again, just like before, we want to put ourselves a little piece of dy because that defines the entire outline of the problem. So remember how our method goes. Now we can set up the structure. This time it's 2 pi times the integral, basically one thing times another thing, dy. Now we can put the bounds for y because we know in this region it goes from 0 to 2. I generally put them on at the end. So we need 2 different values. We need this width or height, and we need that distance of a radius. All right, since we're going about the x-axis, the distance here, this is the easiest way to see, we're saying it's some distance above the x-axis. Well, the distance above the x-axis is just a y value. So big R here, I'll put the R above this, so we're going to use H there, is just y. And that should make sense. Anytime you're measuring from the x-axis up or down, that's a y value. If you're measuring from the y-axis left or right, that is an x value. So if you're measuring from either the x-axis or y-axis, I'm going to help you. Big R is either x or y. All right, what is the height here? How do I find the length of that? Well, since we have 2 different x values, kind of like here, if I have x value of 3 and x value of 10, what's that distance? You do the right x value minus the left x value. So the right x value here is 4. What's the left x value? Well, the left x value is the curve. Now, I know on that curve, x is equal to y squared. So it's going to be this x value minus that x value. So the height of this is 4 minus y squared. Now again, we said we knew the bounds for y. This goes from 0 to 2. Okay, now it's a Calc 1 integration problem. Distribute that out, integrate top endpoint minus the bottom endpoint, and you should get the exact same volume that we did using the shell method. All right, let's see if we can set this up the other way. Let's say if we go about the y-axis. Let's see what happens there. All right, I'm gonna erase this picture just so I can draw the exact same thing again. So there's our 4, there's our 2. This time we're going around the y-axis. I remember our representative rectangles are drawn parallel to the axis of rotation this time. So in this case, we get a little piece of dx. We need that because that tells us our entire structure. So this is 2 pi times 2 functions, in this case, dx. Now again, we can go ahead and put the bounds for x because we know the bounds for x for this region goes from 0 to 4. All right, the two things that we need r, which is the distance from the axis of rotation out there, and we need the height or the width of that rectangle. Now r, since we're measuring from the y-axis, that distance from here is just x. So that is x. For our radius, our height, so since we're talking about up and down, it's going to be the top minus the bottom. Same idea if I just turn this on its side. So it's going to be the top y value minus the bottom y value. Well, the top y value is the curve, and I know on that curve we know y is equal to the square root of x, and the bottom would be 0. Now, of course, you don't need that minus 0, right? So this is y is equal to square root of x, and down here this is y equals 0. Just so you can see it if you're really thinking about it. So top curve minus bottom curve, or right curve minus left curve. All right, so just another method. Now, why would we need two methods if the washer or disc method, whatever you want to call it, worked out just fine? Well, let's take a look at a couple of instances to where having two methods makes our life easier, and sometimes not only easier, doable. Sometimes without another method, you can't actually solve a problem. So let's take a look at, we did this one last time also. We had x squared plus 1, y equals 0, x equals 0. I think it was x equals 2, doesn't really matter. So if we sketch this region, again, we did this last time, it looks something like this. So if you're not sure how to sketch that region, watch the video on the washer method. Okay, so this was our bounded region. So this was x equals 2, that's 5 up there. Of course, that's at 1. Okay, so if we were to take this and revolve this around the y-axis, let's take a look here real quick at what happens. So I'm going to go ahead and just say about the y-axis. Well, excuse me, last class we saw, if we wanted to do this doing the washer method, I'm kind of going backwards here, our representative rectangles are perpendicular to the axis of rotation, which means we have a little piece of dy. But the thing we ran into with this problem is we actually had to do two separate integrals because, in this case, the left side of the representative rectangles changed curves. So we ended up with this, pi integral big R squared minus little r squared dy plus pi integral big R squared minus little r squared dy. And let's take a look at both regions. Need a little bit more room there. All right, so let's say for the bottom region, it goes from 0 to 1. Big R is the distance from the axis of rotation over to that edge. That is 2. Little r is the distance from the axis of rotation to the inside edge. Since it's touching the inside edge, that would be 0. Then from the region from 1 to 5, so this goes from 1 to 5. Big R is the distance from the axis of rotation to the outside edge. That is 2. And then the distance from the axis of rotation to the inside edge, well, that's this distance here. We need that, since we're going this way, we need that as an x value. I'm sorry, I just lost my brain and stuff. A little piece of y, so what does y equal? Here, y is equal to the x squared plus 1. All right, there we go. That's a y. Now, very good example. My brain just stopped. You can tell it's wrong because these have to be in terms of y. So that's not what we need. Sorry, we need to know this distance here, which is an x value. We know y is equal to x squared plus 1. Solve for x, we get x is equal to plus or minus square root of y minus 1. Since we're on the positive side of the x-axis, we know that we need the positive one. Y minus 1. Brain stopped there for a second. All right, so here we get the square root of y minus 1. All right, that should be what we had for last class. Notice because our representative rectangles changed, we needed two separate integrals. However, if we had used the shell method, our representative rectangles would have been, get that out of here, would have gone this way, would have been parallel to the axis of rotation. In this kind, we'd have a little piece of dx. Now notice, we don't need two integrals for this because the bottom edge of the representative rectangle and the top edge of the representative rectangle always touch the same curve. So when we set this up, again, since we already have our dx, we know it's going to look like this. Function times another function dx. We need r. R is the distance from the axis of rotation over to that. And the height or the width is, say, height or the width of that representative rectangle. So since we're measuring from the y-axis, the distance over there to that would just be x. The height of this is just going to be the top curve minus the bottom curve. So since we're measuring up and down, these are y values. So here y is equal to the x squared of plus 1. Down here, this is y equals 0. So again, you don't need the 0, but this would be x squared plus 1 minus 0 dx. All right, now notice that's going to be a much easier integral to do. By the way, again, remember x goes from 0 to 2. Much easier integral to do than having to do two separate ones. So by having another direction to move in, it gives us an option of which one might be easier. Now, it does take some practice to figure out which one's easier. When you do, you might say, okay, I'm going to do that instead of the washer or the shell method. But you need to be able to set up both methods. All right, let's take a look at one more example here of why we might need another method. Let's say our region was bounded by y is equal to x squared plus x plus 1, let's do y equals 1, x equals 1. That's our bounded region. About, let's go about x equals 1, yeah. Let's do that. I think that'll work. All right, so first thing we gotta do is sketch the region. Now this is one of the harder ones we've had to sketch. So there's our x-axis, there's our y-axis. Let's say here's y equals 1, and here it is over here we have x is equal to 1. So the only curve we don't know what it looks like is, by the way, that's a 3. Okay, the only curve we have is this curve. Where does that go? Well, I can do this. I know where it intersects x equals 1, because if x equals 1, that's going to be 1 plus 1 plus 1, it will be up here at 3. So I know that that's a point on the graph. And let's see, I can probably figure out what happens when y is equal to 1. Let's see what happens there. So if y is 1, we have y is equal to x cubed plus x plus 1. Subtract 1 from both sides. Come on. I get 0 is equal to x cubed plus x. I can factor out, so we get x squared plus 1. So we get x is 0, x squared plus 1 is equal to 0. Well, if we solve this, we get plus or minus I. So those don't actually intersect there. So the only place we intersect these two curves is when x is 0. So that's right there. Now, I know what kind of a cubic looks like, so it's going to kind of join there. All right, so this is my bounded region. That one took a little bit more work to sketch, but a little bit of practice, hopefully you'll be okay. All right, let's say, we're going around x equals 1. All right, let's say that we wanted to do the washer method. With the washer method, our little representative rectangle would go right there. We'd have a little piece of dy. Let's try to take a look at this real quick. So if I tried the washer method here, this would be pi times the integral big R squared minus little r squared dy. Now we can see that y runs from 1 to 3 in this region, so we can put that in if we want. All right, big R is the distance from the axis of rotation to the inside edge. Well, since it's touching right there, that would be 0. The distance from the axis of rotation to the outside edge, so little r is touching, that would be big R. Okay, so what's that going to be? Since we're going this way, we're looking for what x equals. So it goes from x equals 1 minus whatever the curve is. So I need to take this and solve for what x is equal to. Unfortunately, we can't do that here. Now, technically you can, since it's a cubic, technically we can solve for x. But this is about a page and a half long of radicals and horribleness. So it's not easy to solve for x here for the function that we need, right? Because we need to know what x equals, because it'll be this x value minus whatever that x value is. So since I can't solve for x, I don't know what to put in there. Or at least I can't reasonably solve. Sometimes you can't solve for x at all, or whatever letter you're trying to. So the washer method can't really be done. However, the shell method, let's just change this up just a little bit. Our shell method. Now our representative rectangles go parallel to the axis of rotation, and we have a little, a little piece of dx. So for the form here, we have 2 pi times the integral function times another function, dx. We can see in this region, x goes from 0 to 1. All right, first thing we need what r is. R is the distance from the axis of rotation over to the curve. Since we're measuring from x equals 1, it's going to be 1 minus whatever that x value is. So there's our r. The height of this is just going to be the top curve minus the bottom curve. So the top curve here is the cubic function. I'm going to get more room here. So this is going to be x cubed plus x plus 1 minus what y equals on the bottom curve, and y equals 1 on the bottom curve, dy. All right, a little bit uglier, but notice this one's actually doable. Combine-like terms, distribute everything out, use your power rule, fairly straightforward. So the only tricky part about the shell method is since we're not going around the x-axis or the y-axis, it's going to be the axis minus whatever that distance is. Because remember, over here, I'm not going to use 1 just for a bigger number. If we're over here at 7 and I want to know how far away this is, you would go 7 minus 3 to get that distance. If I don't know what that distance is, but I know it's some x distance, it would be 7 minus x. And of course, if that x value was 1, it would be 1 minus x to get that distance. Okay, so that's it. That's why we need more than one method to do. So most of the time your book's going to tell you solve this using the washer method or the shell method, but for most of them you probably should be able to do both.